Swayam Prabha. Digital India. Educated India.
Okay, so let's get started with today's class. If we recall what we are doing, like we were looking at the controller block, right? So that's what we started off yesterday. So we looked at the controller as an entity to which we give the error as the input signal, and we obtain the control input as the output, right? And the controller transfer function was C of s, so U of s was taken to be C of s times E of s, okay? So we discussed like three types of, I would say, like fundamental controllers, right? The building blocks. So what we called as a proportional control, integral control, and derivative control, okay? And if you go and look at practical implementation of derivative control, right, which is what we stopped with yesterday, like you will see that in many cases, like they would use a block like KDS divided by TS plus 1, right? So if you even check this out, right? So that 1 by TS plus 1 would act like a low pass filter, right? So to filter out the noise signals, right? So that we discussed yesterday, right? Because one limitation of derivative control is that it can accidentally amplify low amplitude, high frequency noise. Okay, that comes up during practical implementation. Okay, so that's an issue with derivative control, right? So for that purpose, like typically the signal is filtered out, right? Okay. So let's continue from here. Like by and large, like one starts with proportional control. Okay, and if things do not work out, like then what we do is that like we try out proportional and an integral control. Okay, so what is called as a PI controller. Okay, if proportional controller, like for some reason doesn't work, we can try the integral block alone. But we would, as we discussed, if I use the integral block alone, like I'm going to introduce a open loop pole at the origin, right? That's something which we discussed yesterday. So we'll see later that, like if I introduce an open loop pole at the origin, like there are going to be some difficulties, okay, in designing the closed loop system and making it stable. So consequently, one alternative is to use a PI controller, and then we'll see that, like how it helps in solving that issue, right? So as the name indicates, a PI controller essentially has two components, right? The control input is essentially the sum of the proportional part and the integral part. Okay, so that's what it just implies. Okay, so as essentially one can interpret from its name, right? So consequently, the controller transfer function is going to be Kp plus Ki by S. So this can be rewritten as Kps plus Ki divided by S. Okay, so we see that immediately we introduce an open loop pole at 0, but at the same time we introduce an open loop 0 at minus Ki by Kp. Okay, so you see that the controller block will introduce this open loop pole and open loop 0, right? So as far as the PI controller is concerned, right? So this is the transfer function of a PI controller. Okay, so that's the controller transfer function. Okay, and we can see that this is just a addition of both blocks. Okay, so it will basically combine the features of both P and I. Okay, so that's the advantage. And at this juncture, like there is something called as a controller parameter space. Okay, like so. So what is this controller parameter space? So or control gain region. Okay, it indicates. It's used to indicate the feasible region, right? So the feasible region or regions, okay, of the controller gains to achieve closed loop stability and performance. Okay, so that's what we would call as the controller parameter space. It's just a graphical representation, okay, like of what happens. Okay, so in the case of just P, I and D, okay, there is only one controller parameter, right? So that's a real number, right? So this controller parameter space will be a 1D space, okay, like essentially it will be a one-dimensional plot. Okay, so if you want to have a graphical representation, let me scroll up, I will come down. So in this case, the controller parameter space is just going to be a line where you indicate, what are the potential values of Kp, right? Similarly, like if we deal with the integral controller, like once again, the controller parameter space is going to be a line, like where you just indicate what values of Ki will satisfy stability and performance requirements of the closed loop system, obviously. And with the D controller, like once again, we plot Kd, right? Because that's a controller parameter or controller gain in that particular case, right? But when we come to Pi, what happens? This controller parameter space becomes two-dimensional. Okay, so what we need to do is that we need to plot Kp and Ki, okay, to do the job. Okay, so essentially this becomes a two-dimensional plot wherein like we graphically represent what are all the feasible values of Kp and Ki, right, that would achieve closed loop stability and performance. Okay, so that's something which we are going to do, right? Okay, so that's what we call as the controller parameter space. Okay, and the next controller which is typically used, by and large, derivative control is hardly used alone due to the reasons that we discussed. Okay, so by and large it's combined at least with a proportional controller and typically used. So the control input in this case, once again, I'm sorry, what is it?
I didn't understand what is controller parameter space.
Controller parameter space is just an a graphical visualization of the feasible regions of the control gains which will achieve closed loop stability and performance. We are going to plot it. Okay, I've just introduced the term to you. Okay, so if I ask you to essentially construct the controller parameter space in a problem, you need to essentially draw a plot and show what ranges of these control gains will achieve closed loop stability and performance. We'll do it. Okay,
What is closed loop stability and
we are going to look at it. Okay, I'll come there, right? So closed loop stability is something which we already discussed, right? So closed loop stability means I want my closed loop poles to be in the left of complex plane. Okay, question is that like what values of the controller gains would do the job, right? So that's closed loop stability. And once again, closed loop performance would be specified by various parameters that we have learned: time constant, settling time, peak overshoot, rise time, and so on, right? So once again, we will see how that is reflected in the design process. Okay, we are going to look at all those concepts. Okay, so a PD controller, as the name suggests, like has these two blocks, proportional plus derivative. Okay, so consequently, the controller transfer function is just the sum of the two individual controller transfer functions of proportional and derivative control. Okay, so we can immediately see that this introduces an open loop 0 at minus Kp by Kd. Okay, so please remember, like, why am I calling it as open loop 0? Like, let's go back and ensure that all of us recall it. The open loop transfer function is going to be g of s times h of s, right? If you recall from what we defined earlier. So open loop transfer function, right, is g of s times h of s. So that's going to be c of s, p of s times h of s, right? So you can see that it's the product of these three transfer function blocks, right? So immediately, depending on what plant transfer function is something which we have already looked at, right? Feedback path transfer function h of s is typically given to us, right? We know what it is. So controller transfer function is what we choose, right? And depending on what is chosen, right? So the open loop poles and open loop zeros will be affected, right? So immediately we see that, like, depending on the choice of my controller transfer function, I may introduce certain open loop poles and open loop zeros. Okay, that's why I'm writing it like this, right? So in the case of a pure derivative control, please note that, like, we are introducing an open loop 0 at 0, right? Correct? So in the case of integral control, we are introducing an open loop pole at 0. In proportional control, we are not introducing any open loop pole or open loop 0. Okay, so that's what we are doing, right? So essentially, in the case of proportional plus derivative control, we introduce an open loop 0 at minus Kp by Kd. Okay, so that's a proportional control. So once again, if I want to plot the controller parameter space, it will be a 2D plot, right, with Kp and Kd, okay, being the two axes, right? So that's what will happen with PED control. Okay, then in general, we can combine all the three blocks, right? Proportional, integral, and derivative, okay, which is called as PID in general. Okay, so what is a PID controller? As the name indicates, u of t is going to be equal to Kp E of t plus Ki integral 0 to t e tau d tau plus Kd dE dt. Okay, so that's what is a PID. Okay, it's just the sum of the three blocks, right? So consequently, the controller transfer function will be Kp plus Ki by s plus Kd s square. Okay, so we can immediately see that this introduces two open loop zeros, right, which depend on the values of Kp, Ka and Kd, right, because once again you can see that the numerator polynomial of this transfer function is of order 2, right, denominator polynomial is order 1. Okay, please remember that, right, once you take LCM and calculate it, right. And so consequently there are going to be two open loop zeros that are going to be introduced, and it introduces an open loop pole at the origin, right. So that's the PID controller in general. Okay, so now there are three parameters to design, right. So Kp, Ki and Kd, right. So the complexity keeps on increasing. Please remember, each of these parameters is a real number, that can vary between minus infinity to plus infinity. Like we will see that this is going to be very difficult, right. If I want to figure out in a three-dimensional space, right, what will be the feasible region that would essentially work for me, right, for my control design. Okay, so the complexity keeps on increasing. Of course, I combine the benefits of the three blocks, but then there is a price to pay, right, due to that. Okay, so that's what is PID control, okay, in general. So we would be focusing on these blocks for most of our discussions, like for the simple reason is that, like, almost a overwhelming majority of controllers that are used in practical applications, like belong to this class of PID controllers. Okay, and later on, like if time permits, we will also look at other type of controllers, what are called as lag compensators, lead compensators, and lag lead compensators and all. Okay, so we'd come to those controllers later on, right? So, but then like by and large, we are going to look at PID control, and we'll learn how to design such controllers. Okay, so now let me start doing some examples that will also motivate the topics which are going to come ahead, right? So let's do a few examples, and then like we will discuss them. Fine. So any questions about at least the realization of the PID control? It's pretty simple, right? So that is, we discuss the building blocks, you just combine the building blocks, like as and when we want, right? So let's do some examples. Okay, so I'm going to draw block diagrams and also like write things in a methodical manner, like I would strongly suggest that you also follow that. Okay, so that like we just follow a template. It's not necessary, but that way we will make sure that we don't make any simple mistakes, right? So let us say, we are given a plant transfer function which is 1 by s minus 1, right? Let's say P of s is 1 divided by s minus 1, right? So what is the order of the system, order of the plant? First order plant, right? Right? So is it stable or unstable? Unstable. Why? Since it has a pole at s equals 1 is its pole, right? Okay, so the pole is in the right of complex plane, so obviously the stability is not lost, stability is not there, right? And one purpose of feedback is also to ensure that we stabilize an unstable system, okay, to begin with. Okay, so that's also like one reason why we design closed loop control systems with feedback. Okay, so let's try to design a closed loop negative feedback, unity negative feedback system. Okay, so as a common condition for all these examples, let us consider, it's not always necessary, but here it's we consider, let us consider the design of a unity negative feedback closed loop control system. Okay, so that's what we are going to do. Okay, so let us say, we want to design this system, right? So what we do is the following. So this is y of s, okay, and the input to the plant is u of s, right? So let's say I have a reference input r of s. So what we do is the following. So I close the loop. Okay, unity feedback means this is not unit, sorry, unity, please correct it. Okay, so this is the let us consider the design of a unity negative feedback. Okay, not unit negative feedback. Okay, unity negative feedback. So I hope it's clear what those adjectives means, right? Before feedback, if I put unity, that means h of s is 1, right? Negative feedback means at the summing junction I am subtracting these two signals. Okay, so that's what it means, right? So let's say, I have an error measure, then I need to have the controller transfer function here. Okay, so that's what we have. So P of s is 1 by s minus 1, right? We are given that h of s is equal to 1. Okay, so now let us try a proportional controller to begin with, right? So and then see whether it works or not. Okay, so as a first step, let's try proportional control. So this implies that g of s is going to be equal to c of s times p of s, and that's going to be equal to kp divided by s minus 1, right? Do you agree? Okay. So, this implies that the closed loop transfer function, which is nothing but y of s divided by r of s, that is going to be equal to g of s divided by 1 plus g of s h of s, and that is going to be equal to kp divided by s minus 1 divided by 1 plus kp divided by s minus 1, right, because h of s is 1. Okay, so that is what we do, and if we simplify this, what will we get? We would get kp divided by s plus kp minus 1. Okay, so this is the closed loop transfer function. Okay, and how do I find the closed loop poles? I need to find the poles of the closed loop transfer function. So, I look at the denominator polynomial of the closed loop transfer function. That is what is called as the closed loop characteristic polynomial, right? And then I have to solve what is called as the closed loop characteristic equation, right, which is the denominator polynomial equal to 0, right, to figure out what will be the poles of the closed loop transfer function, right. So, this implies that the closed loop characteristic equation, which is given by s plus kp minus 1 equals 0. Okay, if I solve this, we immediately see that the closed loop pole is going to be at s equals 1 minus kp. Okay, so this implies that for closed loop stability, okay, in other words, stability of the closed loop system. Okay, what we call as closed loop stability means it's stability of the closed loop system. For closed loop stability, what should happen? See, I want all my closed loop poles to be strictly in the left of complex plane. So, I want, there is only one pole, obviously it's a real number because kp is a real number, right. I want that to be negative, right, on the negative real axis. So, when will that be negative? Kp is greater than 1. So, we see that, like we have found the range of kp which will essentially achieve stability of the closed loop system, right. So, this is a very simple example. So, if I want to draw the controller parameter space now, so this is just how we draw this, right. So, essentially I draw kp, let us say this is 0 and let us say this is 1, right. What is the feasible region? It is all this region to the right of 1, okay. Kp greater than 1 is my feasible region, okay. That is just a graphical representation of what is the feasible region, okay. So, this is the controller parameter space for this example, okay. So, it gives us, okay, what values of kp can I choose, and now the question arises, okay, how is this analysis useful, right, because just imagine that, like you have a machine or system, which has this transfer function, right. So, let us say, like by this analysis, however approximate it is, what have we done? We have converted a parameter which can essentially take a value between minus infinity to plus infinity into a parameter whose range is between 1 and infinity, right. At least we have narrowed down the range, okay. So that we do not accidentally choose a value that might make the system unstable, right. So, let us say, like you give me this plant and you ask me to make sure that I design a feedback system and stabilize it, okay. Without this analysis, let us say I have a system and then I program kp equals minus 10, what will happen? The closed loop system will be unstable, right. But at least rather than doing that blind trial and error method, at least through this approximate analysis, I have figured out that, okay, let me choose a value of kp which is greater than 1. At least I am assured that, in the presence of all these approximate analysis, at least kp greater than 1 would give me closed loop stability. And we would later see that if I want to incorporate closed loop performance, this band will even reduce further. Okay. So then what, for example, like this band may be reduced, now the range is between 1 to infinity, right? It may reduce to 1 to, let's say, 95. So at least like I have a narrow range to work with. Okay, then I go to the experimental system and tune, right? And then I have to fine tune my gains. Okay, that step is all, what to say, is a final step which we always need to do. Okay, because we remember that like all the analysis that we are doing is all approximate, right? So we are approximating the practical system as a linear time invariant system and then doing all this analysis, right? So we have to give some tolerance to those approximations. Okay.